Just to let everybody know where we're at today, you probably know me as the Phoenix guy from all these years. As of April this past year, we no longer rep Phoenix Controls. We've picked up Price Critical Controls, and as of the last few weeks ago, Price Critical Controls is now Antec Controls by Price Industries. So just to add confusion to the whole thing. But anyway, from Phoenix to Price to Antec, whatever systems you have, I'll be involved with those, or have been involved with them. So my plan today is to go through laboratory airflow control, some of the different flow components, fume hoods, and just normal or regular airflow controls inside labs for the entire space. That's the plan today: introduction, airflow control valves, fume hood controls, room pressure and temperature control. Again, like the other speakers, if you have any questions, just ask up, slow me down at any time. So to start with, your different laboratory airflow controls, or just control devices in general. You have on the top is a regular terminal box with the cross flow sensors. In the middle is a Venturi valve with airflow measurement, and in the bottom is your Venturi air valve, mechanically pressure independent cone with no airflow measurement, position control. When you're talking about airflow control devices, you're looking at mechanical operation, your flow and pressure ranges, control methods, your control accuracy, speed of response, which become critical in laboratories, your maintenance, sound, and coatings for different applications such as your fume hoods. We start talking about accuracies. You're looking at your standard accuracy valve or damper would be your cross flow sensor with a damper that's adjusted to maintain your airflow. Direct airflow measurement using a device in the airstream. Your turn downs are relatively low at 6:1 and typically require some amount of duct diameters to get you the clean airflow for measurement. The next level of airflow control valve would be the high accuracy damper control, where we're measuring velocity ports across the Venturi or at the inlet Venturi using a transducer to control the damper for airflow control. So you still have direct flow airflow measurement with velocity pressure. Other devices are vortex shedding sensors, and thermal dispersion give you the same type of control. Your turn downs can increase with this type of control upwards of 10:1, and your duct diameters requirements are reduced from 3 to 1 straight duct diameters. And then the final device, which we're going from least accurate to most accurate, would be a straight Venturi valve, mechanically pressure independent setup, such as your Phoenix valve and your Antec airflow control valve. You're looking at airflow turn downs in the range of 16:1, and inlet and outlet duct diameters not required, since we're not measuring actual airflow. The flow is controlled through electronics with the flow curve, which will come up. So if you start looking at the internals of your Venturi air valve, mechanically pressure independent, you can see the two different examples here of 1-inch differential pressure and 3 inches differential pressure, where the spring inside the cone is compressed more with 3-inch differential as opposed to the 1-inch, but the airflow is still maintained at the same volume of air. The spring allows the cone to move inside the Venturi to have a smaller opening to give you the same airflow at both 1-inch and 3-inch. When it comes to operating ranges, talking back now to your cross-flow sensor type device. And as you see, is your size 8s, 10s, 12s, 14s, your flow ranges, min-max, and your turn downs are roughly 6-to-1 in that setup. As you move to the higher actuator control valve, where you're measuring the velocity pressures with the transducer, your flow ranges are roughly the same, but your turn downs, you gain turn down ratios up to 10-to-1. And then when you move into your mechanically pressure independent Venturi valve, your airflows have getting wider depending on low pressure or medium pressure valves. If you look down at your operating range, again, since you're not measuring airflow, we're going to need a minimum differential pressure across that cone and spring to engage the spring. The spring has been designed and engineered to work within those ranges, but you got to engage that spring to start pushing that cone into the Venturi to do the airflow control. So your low pressure valves are 3/10 to 3 inches differential pressure. Your medium pressure valves are 6/10 to 3 inches differential pressure. But if you look at the maximum flow range, the low pressure valves get derated to be able to deliver the airflow at the lower differential pressure. The turn down, you lose a little turn down because your maximum flow has been reduced. But you can see a significantly higher turn down when on the Venturi valve. And this becomes important in laboratories where we got fume hoods, where we have to adjust the supplies and general exhaust based on fume hood demand. So turn downs become very important inside a lab control. So the control methods in these three examples, you got your blade damper with the cross flow sensor is a closed loop control where you're measuring the airflow, you're sending the signal through the controller, drives the actuator, continually and measures the airflow after the movement, and finally finds a set point based on the signal that's required. And that process will start over on any subsequent change in flow demand. So your velocity pressures are pitot tubes, cross-flow sensors, orifice rings, are examples of the flow measurement for these devices. Pressure transducers have several types of errors that should be considered, and overall flow sensing actually combines the effects of the probe and the transducer. So your probe is sending the signal to the transducer, and both those actuators can add up into error and just add onto themselves. So here's an example of errors in full scale in your velocity pressure reading devices. Obviously the higher pressure or the higher flow range is going to generate a lower error because you have enough velocity pressure to give you a better reading. But as you lower the CFM, your errors start to compound because of the errors in the devices and the transducer and lower velocity pressures. Vortex shedding, which has become popular way in one manufacturer to do airflow control. So I don't know if you've had the chance to work with any of these devices, but it uses a airflow by measuring the pressure pulses or vortices formed on the lead side of the airflow device. So it's controlling airflow with basically two different dampers controlling the airflow through vortices on each side of the device with nothing in the center. Actually, these are somewhere in the 2.5 to 10% range, with shedding sensors down to 450 CFM, or feet per minute, sorry. Thermal dispersion is another means of measuring and controlling airflow. Devices measure airflow through thermistors in the airstream. little better accuracy, plus or minus 3%, reading accuracy down to 50 feet per minute. So we get into flow characteristics of controlling flow in these different applications. So with the blade damper, the flow control application actually depends mainly on the airflow transducer, but the resolution blade damper will greatly impact the flow measurement and accuracy at low flows. So as we've all seen in air measurement, airflow control, on a blade damper, your airflow gains really quick at the bottom end. So as the damper starts to open, you get a huge amount of your airflow from 0 to probably 25, 30%, and then the rest of the CFM will come out as you fully open the damper. But it's difficult to control airflow in that small amount of range of opening, from 0% opening to 10 or 15% with huge amounts of airflow increase at that point. So the open loop control, again, back on the Venturi valve control type, where you're mechanically independent control from the actuator to the flow to the valve. The open loop control drives the link between the controlled variable and the controller. So open loop control anticipates the effect of the external variable on the system, adjusts the set point to avoid excessive offset. So the position of the airflow, the position of the valve inside is dependent on the airflow curve. So the actuator is going to drive the shaft to position for a CFM, and the pressure-independent spring inside that cone is going to allow that CFM to be maintained with static pressure changes in the duct. So with no movement in the shaft, that device will maintain the same CFM as pressure changes in the duct due to external forces in other labs or other spaces changing the duct static pressure. So the flow characteristic of this type of device is what I'll refer to commonly as low and slow. It'll start out, the CFM will start out low, and it'll increase parabolically as you move from 0 to 100%. So your flow maximum doesn't occur, or the large percentage of your flow doesn't occur at the start point, but it occurs as you further stroke the valve towards its full open position. So you get a nice smooth airflow change throughout the full travel of the valve or the shaft on the actuator. So again, this is just another representation of that concept. With open loop application is driving the position of the valve, and the flow is nice and stable as you move from full close to full open. Again, it's another example of airflow sensing, controller moving the damper, and speed of response. So the speed of response on a device where you're measuring the airflow and adjusting the damper has got to be fairly slow, or you'll get fluctuations around your set point that you can't meet. You'll overshoot and undershoot and have to keep resampling to get it to set point. So the speed of response when you're measuring airflow has to be fairly slow so that you can let the damper react, get another reading, and then finally hit your set point. In the Venturi air valve, where you have, again, you're mechanically disconnected from the actual flow, you're going to position your control arm based on the potentiometer feedback, and as soon as you reach your flow set point, your actuator stops moving and the valve is positioned. So the speed of response is as immediate, as fast as the actuator can move it to the position you deliver the flow. Again, internally the spring inside that cone will maintain that flow with no further movement in the pivot arm, the actuator position of the valve. So speed of response in laboratory ventilation is VAV response should be sufficient to increase or decrease the flow within 90% of the target flow or face velocity in a manner that does not increase potential for escape. Response time should be less than 3 seconds after completion of the sash movement is considered acceptable for most applications. Faster response times may improve hood containment. So the ANSI's document states 90% of flow and within 3 seconds after movement of the sash. So another speed of response, this is the ASHRAE standard. The sash shall be fully open and smooth. So when you're testing fume hoods, it states that the way you're supposed to operate the sash on a fume hood is fully open and smooth motion of velocity between 1 feet and 1.5 feet per second. Basically saying you're not throwing the sash full open as quick as you can or lowering it as quick as you can. There's a procedure for opening and closing the sash for testing. The time it takes from the start of the sash movement until the sash reaches the top, and the time it takes from the start of the sash movement to the face velocity reaches or maintains within 10%, design of the face velocity should be recorded. So again, it's sash movement from the time it reaches the top and from the start of the sash movement. Okay? So in VAV fume hood testing procedures, look at there, a NEB document. VAV hoods are also to be tested and determine response time to return to near steady state condition after change in sash position. When changing sash position to smooth continuous motion, measure and record, report the VAV speed of response time to first obtain a velocity equal to 90% of the baseline for each iteration. So this is right out of the NEB standard for fume hood testing. But again, the part that's important here is after change in sash position. So after the sash has started to move is when these measurements need to be recorded. So here is a graph of sash start and the timing associated with getting the airflow to set point. Venturi valve, sash, you see the sash starts on the red line. The airflow is shortly behind it, and when the sash stops at roughly 1,000 CFM, the airflow is right on top of it within 0.8 of a second. That's from time of sash movement to sash stop, the airflow is met. So speed of response testing from the time start of sash movement in seconds to CFM, so sash movement. It's the same graph, but now this is timing the speed of response. So from the time the sash started moving to the time it stopped moving, how long it took for the airflow to get from its start point to its end point, to 2.5 seconds. And the documents call for less than 3 seconds here. So on the high accuracy control valve is where we're using velocity pressure to measure through a transducer. Vortex shedding would be a similar, thermal dispersion would be a similar device where it's, again, the same graphs, but back to sash movement to airflow. Reaching airflow is 1.25 seconds. The Venturi valve was 0.8. Again, it's stating in the documents to be less than 3 seconds. So still does very good control of getting the fume hood to its control point. On the speed of response, from the time the sash starts moving to the time the sash stops moving and the flow is stable, is 3.1 seconds. Again, fairly acceptable when it's less than 3 seconds. I guess you could split hairs on that. Somebody might have issue with that, but still very good response time on those type of devices. Cross-flow sensing device in this application, I don't even have a chart for it, but it's way outside these time frames. So here's a couple of different, airflow devices. There's your vortex shedding device. You can see in the center section it's kind of blocked out. It's got a flow sensor on either side. That's and a damper that's opening and closing, and that flow sensor is driving that damper to maintain flow. The top one's your cross flow sensing device showing the removable panel for cleaning, which is very important to consider, or at least have knowledge of, because you're probably not doing the design. But cross flow sensors, are going to get clogged by whatever comes through that duct. Vortex shedding devices aren't as bad, but they do have removable plates on those devices too, for the same reason. The Venturi valve with no flow measuring devices doesn't have the need for cleaning. So there's an example of buildup on a cross flow sensor. That's showing a chem wipe. That's a device that could be sucked up in a fume hood. You have your hospital rooms, your bedding every day. They're changing the bedding, or twice a day, or who knows, whatever the frequency is. But anyway, they're bringing bedding in. Bedding is letting off lint. As soon as they make that bed up or throw the old sheets off, put the new sheets on, lint continuously cycling through that room. Well, it's going up into the duct, and it's going to cake at some point in time, continually add to that flow ring or that flow sensor device. And as we know, if that thing starts to clog up, the sensor is no longer going to give a valid reading. It's going to say the flow is low. Well, if the flow is low, increase damper position, open, open, open. So all of a sudden, you're going to have inaccurate flow readings. Your damper's wide open because you think your flow is low, and now your system is out of control. The room is no longer in control due to a bad flow reading. The control system doing what it thinks it should be doing based on it's the sensed variable. So that was pretty quick through control devices. Is there any questions or comments about that? I went through 3 different types. They're pretty standard though, as far as the cross flow sensing, the velocity sensors through a transducer, and then the pressure independent Venturi valve. So just moving into a little laboratory control devices, such as fume hoods. Probably all seen, different fume hood types. You have your louvered front panels, and this is just showing sash closed on the left, how air would go through the hood, sash open on the right, where the sash will come up behind the louvered panel and block most of the airflow through that panel. It's not going to be 100%. Normally see that in a constant volume. Let me back up. We'd prefer to see that only in a constant volume fume hood. Unfortunately, most sites buy fume hoods with louvers for variable volume application. So we're going to lose airflow at the top. Normally not enough to prevent the fume hood from performing, but it's something to note that, that's in a variable volume application. We're trying to take everything through the sash opening with no losses anywhere, and that louver will cause losses. Such as restricted bypass or a VAV hood. There's no louvers in the top. All the air comes through the sash or through the airfoil at the bottom, and allowing for much better, I say containment, but the air to come through the sash when it's open. So you can see the differences here. Lot less airflow or eddy currents in the fume hood when it's closed, and when the sash is open, your airflow is coming through the open area of the sash, maintaining safe fume hood capture in a variable volume application. Next couple of slides are just showing, different types of fume hoods: vertical sash, vertical only. Again, it's got the bypass louver at the top, airfoil at the bottom. When we set up fume hoods for control, we know the sash is only going to move from that airfoil up because it can't go any further. But that airfoil is a certain volume of air. It's got an area to it, so we're going to get air through there also. So we calculate that into when we're setting up these fume hoods for the total airflow based on the sash height. We use that airfoil as part of the amount of the area of the hood for the amount of CFM that's going to be exhausted through that fume hood. We don't account for the louvers initially, but I have seen cases where the louvers did have enough air going through them when the sash is open to prevent the velocity at the face of the hood that we're all looking for. So then we have to back up and add leakage, lower the sash for a lower sash height. You've got to do something to make the fume hood work, because we're not going to get a different fume hood at this stage. We've got the job what we got. Here's an example of a combination fume hood, vertical and horizontal sashes. Just another challenging VAV hood, because you have to be able to control the airflow with the vertical and the horizontal at the same time, meaning partial horizontal open, partial vertical open, independently, whatever's necessary for that fume hood use by the occupant. So again, I'm working on the Antec equipment. Our solution for vertical only hoods is we use a vertical sash sensor. We attach it to the vertical sash through, either the cable on the top, whatever means we can attach that sensor to monitor the movement of the sash. So that's a device. It's a resistor. It attaches to the sash, put a voltage in, get a different voltage out based on resistance, and we'll monitor the sash movement. That's just showing the top of the hood. So a typical place to mount that is attached to the counterweight cable to monitor the movement. So sash position sensing. Measured open area might not be the actual open area. So, anybody know what I mean by that? When it comes to controlling fume hoods, you got different areas based on the design of the hood itself. So we have a combination hood here where you got the airfoil at the bottom, which is some amount of area. You got your horizontals, which is some amount of area. And if they had a bypass louver on this hood, we'd be having air flowing through the louver too, because until you raise it vertically, the louver wouldn't be closed off. So you'd have air going through that way. So the actual area may not be the open area of the sash. So the way we deal with combination hoods, let me back up. This is just showing a way of monitoring and measuring face velocity for control, as opposed to the sash sensor on the vertical sash. You do sidewall sensing and adjust to the actual velocity reading through the sidewall sensor. So different control methods for hood face velocity control. With sash position sensing, which will measure the vertical motion of the hood. So the advantage is speed. As that sash is moving, you immediately know the movement of the sash, and you can control the airflow and send a signal to the valve for airflow control. Disadvantage is if there was something in the way, you wouldn't know it. Obstructions. The sidewall sensing, if if you have an accurate enough sensor in the sidewall, then it'll do a good job of controlling an accurate airflow. But just like any control device where you're measuring airflow, you're going to have overshoots and undershoots. And in a fume hood, it may be open momentarily and then reclosed, and so you're continually trying to catch and find the set point in a fume hood, unless you just leave it open. So another method is of doing a fume hood with combination sensors is hybrid sensing. So you would use a sash sensor for the vertical portion, and you use a sidewall sensor for the overall reading, and you marry those two together to provide a signal to the valve to position it for airflow based on both pieces of information that are going on. So your sidewall sensing for actual airflow measurement or velocity, and your sash sensor to start the process of moving the valve to the required flow position. So you start moving the sash, you immediately start moving the valve, and then you read the velocity at the same time to know when you've met your set point for velocity. All right, couple questions I've come up with. So I see this all the time in labs. So at what sash height are fume hoods normally certified by a certifying agency? Called a third party, maybe y'all do some third party. What would be the standard answer? 18 inches. What sash height is used for measuring the maximum design CFM for a fume hood during the tab of a project or retrocommissioning? What sash height? Come on, most of y'all want to say 18. I know it because I see it all the time. So the question is, what is the difference between the fume hood certification and the max design CFM testing? So we said the fume hood certifier who's got one job, and that's to check the fume hood at 18 inches. Somebody came up with that number. That's, I guess, because normally where the stops have always been mounted over the years. So they're going to come in and they're going to certify the hood. They don't care if the CFM for that hood was 500 or 2,000. Raise it to 18, measure it, fill out their paperwork, and leave. Either say it was good or not good and cause us all problems. But when we're tabbing a project, that's a different animal. We have a design CFM for that fume hood that goes along with the design CFM for the supplier in that space and the general exhaust valve in that space, and it all has to work together to maintain the lab properly. So, back to the same question. What is the sash height used for measuring the max design CFM for a fume hood during the test and balance process? Sash stop? Yes, sir.
Well, I just finished doing two different science buildings.
Mm-hmm.
And each hood, well, they have two different type of hoods, and each one is different.
Right.
We have 12 inches, 14 inches, 18 inches. And that was the working height of the hood. That's what they were going to use them at.
Right.
So that's how we measured it. That's the working height.
As a certifying agent or as a test and balance?
Test and balance.
So you had multiple CFMs then for that one hood.
They were only using it at one height per type of hood.
Okay.
So we would, for that hood, we would use it, we would measure it at that height. If it was 12 inches, it would be 12 inches.
But the CFM associated with that 12 inches was probably on the schedule for that hood.
Yes.
Okay, so they did their design properly. That's a good thing. It's not seen enough. So when we're looking at tabbing a project, so we're looking at the sash stop, I think a high percentage of y'all would probably say, yeah, probably. 18 inches, okay, that's probably the same as a sash stop. Full open, none of those give you the answer to the question. None of those do. Because they're just a sash position. You've yet to entertain or ask yourself, what's the design CFM for that fume hood? Where do we want to be when we're tabbing the project? So the sash height associated with the max design CFM is Kevin Brewer? Do the math. And it's just math. Y'all do math every day in your jobs. You're calculating, RPMs, belt sizes, whatever, temperature gains. So the height associated with a fume hood, testing while you're, again, a new project where you have to test and balance the project based on the design CFM. CFM times 144 conversion, feet per minute, most fume hoods are 100 feet per minute, times the hood width. That's going to tell you the sash height that hood needs to be tested at. Example, 6-foot hood, 62.5 inches wide, maximum design CFM of 1,000 CFM. 1,000 CFM times 144 divided by 100 feet per minute, 62.5 inches is 23.1 or so, roughly 23-inch sash opening. That's not 18, that's not the sash stop, that's not anything but what the design engineer said he wanted. He wanted 1,000 CFM on that hood. You have to go to 23 inches to get that hood at 1,000 CFM. If you don't, you're going to send the report back through the channels. It's going to come back to me, and you're going to say I'm low. I'm not low. We didn't initiate the sash at the right height to give you the flow associated with that 6-foot hood at 1,000 CFM.
Whose written procedure is that?
Whose written procedure?
Yeah, is that a NEB written procedure? Where is it ASHRAE or?
It's not anything but a design requirement for the project. That fume hood was designed on the schedule for 1,000 CFM. That's a pretty standard velocity for a fume hood. If it was 80, plug 80 in there. If it was 110, plug 110 in there. Exactly. So I think we all agree 100 feet per minute is pretty standard fume hood design point.
So is 18 inches. So 100 feet per minute at 23 tells me the same thing as 18 inches, and I'm running 127 feet per minute.
And you're not going to do that in a VAV hood. A VAV hood is going to maintain 100 feet per minute by its design, by what it's supposed to do at any sash height between minimum design CFM and maximum design CFM. So if you
Find your maximum sash height.
Well, if you walked up to a fume hood and you said, I need to test this fume hood for 1,000 feet per minute because that's the design, and it's a VAV fume hood, and the VAV fume hood's been set up per the project documents for 100 feet per minute. That's its design point from closed or from minimum to maximum. Well, if you only go to 18 inches, you're only going to see 100 feet per minute. And 18 times 62.5 divided by 144 times 100 is 725 50 CFM, not 1,000.
Oh, you're saying the sash position indicator won't allow the VAV to open the max?
The sash sensor is going to tell me that I'm only at 18 inches.
Yeah.
And so 18 times 62.5, which is the width of the hood, times 100 feet per minute gives you CFM. So the sash sensor says I'm not high enough to need 1,000 CFM, so it's not going to go there. So you have to raise the sash to the point necessary for the system to deliver the 1,000 CFM that was the design point. Did I finish answering your question, Rodney?
You did, but I think that's assuming that 100 feet per minute, and the engineer, how do we know as test adjust and balance professionals that the 1,000 CFM isn't at 18 inches and 125 feet per minute?
Because, again, I'm assuming that the contract documents told us 100 feet per minute for the fume hoods as a blanket velocity, variable volume, 100 feet per minute, but my top end of this fume hood is 1,000 CFM. So the only way you can get to that with those parameters, 100 feet per minute design and 1,000 CFM design on a 6-foot hood, is to raise it 23 inches.
Most times we don't have, I'm speaking, and if somebody can disagree with it, but most of the time we don't have that kind of information come from the design team. We'll see 1,000 CFM, and we know the standard is 18 inches.
But I have to know that going in because I have to set this fume hood up for 100 feet per minute, 1,000 CFM. So the only way I can do that is by determining through that equation what this maximum sash height is.
Are they telling you 100 feet
Yes.
Are you assuming
I'm being told.
they're telling?
Right, because I've got a project, I just did Salem Hall, Wake Forest University, and they have some hoods they've got two design points, 65 feet per minute and 80 feet per minute, depending on if it's a chemistry lab or a teaching lab, I can't remember. But anyway, so they told me the value associated with the velocity they wanted at that fume hood. No, you have to know that information or none of us can do our job.
You're just opening that SAS position until you get the rated CFM. You're maximizing the potential, I guess, of that.
Well, I'm only trying to satisfy the engineer's design point. I don't care how I get, I don't really, it doesn't matter to me what it is. But he's told me that fume hood maximum is 1,000 CFM. And so to take this conversation further, if you're trying to balance the entire lab, and this fume hood is supposed to do 1,000 CFM at maximum, if you don't put that at 1,000 CFM, your supply valve, or your supply air device is not going to open to its maximum because it's expecting to see 1,000 to drive it to where it wants to be. So I see where you're coming from. How do you know that 18 is not the place to measure everything? That's why I differentiated between the certifying agent and the tab contractor.
That's why I was asking, is this an ASHRAE standard, does it do that, or a NEB standard, is it addressed in the NEB fume hood performance?
And I think it gets addressed in the certifying, not the TAP. You're talking about as a TAP professional, what are you gonna do?
Right.
And you just made the comment that the TAP professional would say, I don't care, I'm getting design CFM.
But you're not. You never got to 1,000 CFM if you raised it to 18 inches.
Yeah, I did, I had 125 feet per minute.
You're not going to get 125 because I've calibrated my system to do only 100 feet per minute. I'm not going to allow it to go to 125. The setting inside the fume hood monitor is 100 feet per minute. So it's not going to say it can't do both. It can't do 100 feet per minute at 18 when the certifier's there and 125 when you're there doing tab. It can only do one. So it's set to do 100 feet per minute. This is a good discussion, good point, because this is by far a problem.
So should that be a design RFI, that really, that hood is to be tested at 18?
That's, again,
That's the standard.
no, that's the certifying standard. TAB doesn't have a standard. You don't have a standard for 18 inches.
A university has a standard, schools have standards, they tell you to test them at 18 inches. So
That's another entity, the university, the whomever, the pharmaceutical, whatever. But you're taking that as information outside of the design document. The design document told me 100 feet per minute, 1,000 CFM. Until I deliver that to the project, I can't deliver it to the owner. The owner may want something different, but we haven't given him the project yet. I've got to deliver this thing per the contract documents before we get to that point.
I'm saying, should it be a design RFI from an energy standpoint, 18 inches is say 800 CFM?
You're overthinking it. He put out a design. We walked onto the job together, and this is our design.
But we're also professionals, and we should be asking design RFI questions before we just go say, let's go exhaust 1,000 when our fume hoods really only need 800.
But you're saying that from an energy perspective, and the design engineer had another reason for doing this design. So I'm not going to disagree if you want to take and ask the question, but you got to know that this is going on in order to ask the question. And that's why I brought it up.
Right, and that's why we don't want to assume 100 feet per minute, because you just gave us two values, teaching lab versus, right?
But I was given that number.
That's the whole point of the discussion.
Right.
The question has to be asked, there's no such thing as a known, I know it's supposed to be 100 feet a minute, or I know this, or it's supposed to be that.
No, I'm not supposing. I'm saying that these values were given to me by the contract documents. 100 feet per minute, 1,000 CFM. I'm not assuming anything. It says it right there in the document, 100 feet per minute, because I got a VAV fume hood, so 100 feet per minute, and the CFM for that fume hood is 1,000.
I agree. I just think in our discussion, we were talking about some assumptions of 100 feet Like,
Yeah.
we usually see this and that kind of thing, so it leads us down that
I understood, yeah.
to get to 100.
But I'm saying these are in the document. Yes, sir.
To me, it seems like a discussion between, are you testing the fume hood, or are you testing the system it's connected to?
Well, then,
If you're testing the system it's connected to, then you need to raise that hood up to 23 inches so that you've got maximum flow, so that now you've got, you're checking all the way out to the fan, you can actually handle that.
that's part of it, but you're now going back to, again, that's why I had certifying versus tabbing a project. Because I'm not trying to make it any more, complicated than just the design. Again, the designer gave us this information. We didn't tell him what we wanted. He told us. And this is how it gets accomplished. And that's where the confusion comes in the lab, test and balancing effort that we all go through, is that we get stuck on a sash height associated with a fume hood when it's really based on the CFM that's been designed and the width of the fume hood, and the velocity, not just a number, not just a height. Yes, sir.
Is this taking into consideration leakage, other air that's actually going through the fan, which is coming out of that room? Because this, what we're talking about, you're acting at 23 inches of absolute, but there's other areas where air will be able to get into that hood.
Well, this is the control CFM for the equipment in the duct that's going to deliver 1,000 CFM. So anything else coming in the room doesn't affect what's going through that hood.
About leaking around the cabinet, it's bypassing.
Or you mean around the cabinet itself?
So the only real way to do it is go up there and try to.
Well, I'll give you that every day and twice on Sunday. Give me a traverse of 1,000 CFM. That's what I want. But the only way you're going to get to 1,000 CFM is if you raise that hood to 23 inches because it's a VAV hood. And a VAV hood has a velocity set point from the sash movement. So the velocity doesn't go up based on sash movement like a constant volume hood. It maintains 100 feet per minute as you change the sash position. So this, like I said, this becomes, this goes back to what you were saying, where you don't get the supply air quantity you want because the sash, you only raised it 18 inches, the supply didn't go up, the general exhaust didn't react like it's supposed to because you didn't go to 1,000, you only went to 18 inches, which is, I think it calculates to 750. And so it just kind of gives your report all kinds of holes. And then you send it back to me, and I say, well, where did you take the hood? Well, 18, well, to get 1,000, you got to go to 23 inches. So then you have this whole conversation. This was especially put in here for this discussion because it is, engineers have started doing the math properly and coming up with 18 inches, but it's not always the case. Yes, sir.
Why don't they have this part of a fan log?
Sir?
You know how like we have a fan log sheet? Why don't they have this on like a fan log sheet?
You're talking to somebody, I couldn't even begin to answer that question. I mean, again, I'm just taking stuff right off the schedule for the project, for the contract documents. And, yes, sir.
I do probably 90% of my work is done directly from the owner.
Mm-hmm.
The owner tells me I want 80 feet a minute or I want 100 feet a minute at 18 inches. So I balance it like you just said. And Mike's going to have to come back after he tells me, he says, no, you got it wrong. You got 125 feet a minute. We only want 100.
Well, you're only going to have 100 at 18, but you're only going to have 750 CFM instead of 1,000. So yeah, you're still going to have 100 at 18. I've done some projects where the CFM calculated out to 14 inches. Okay? So now the design was 600 CFM instead of 750. The math gave me 14 inches. Y'all come in and raise it to 18 and fail it because it's low. The reverse is a problem too, because you'll send it back to me and say, Dean, you didn't meet the velocity. But I met the CFM. The document says 600. I gave you 600. We didn't design it properly.
But from a safety standpoint,
I'm only looking at contract documents that I got to deliver the project to. I do it all the time.
So, you know, if it's 14 inches and they're gonna operate at 18 inches, somebody's not gonna be protected.
I do it all the time, and you wouldn't believe the number of deaf ears that falls on.
But is it documented?
Oh, absolutely report it. Because just like you're all saying, we got to deal with this in the end. Somebody's going to have a reckoning with this. And it's not going to be the engineer most likely or the mechanical contractor. It's going to be us. And so I make sure people are aware of that situation. So
We've got a lawyer speaking to us out there.
Mr. Brewer.
What about when you hit the emergency button? Talk about that.
I can talk about that. So on the fume hood monitor, you'll have an emergency button that will drive the valve to its maximum CFM, design CFM, 1,000, regardless of the sash position. So back to this gentleman here, when he said, I want 125 feet at 18 inches, if you push the emergency button, you'd probably get that. But I'm trying to be not trying to override things. Most people want to test the project based on automatic operating modes. I mean, that's what we're going to deliver. So, it's a great discussion. There's a lot of good points that come out of it, but we've got to make either an RFI or decisions based on the information we're given. And if we think it's an issue, let's just maybe say it that way, with the information we're given in the contract documents, we need to speak up. If there could be an energy concern, there could be a sash height concern, there could be many things. We all know in the heat of battle, trying to deliver a job that's already 6 months behind, we're probably not going to want to be taking the effort to write RFIs. But this is how you're going to figure out the sash height associated with these known parameters that are part of the contract documents. Let's leave it at that. The 100 feet per minute is specified and the 1,000 CFM is specified. And that's how you're going to get to that point.
It sounds like this is solely talking about flow measuring lab hoods though that are reading feet per minute.
That's exactly what this is referencing,
And that's the essential difference right there,
as opposed to,
as opposed to just a constant volume hood where you're gonna set it.
oh yeah, oh yeah.
Feet per minute or whatever cycle.
These are variable volume fume hood requirements. A constant volume, that's a done CFM. You're going to use the same equation to calculate the velocity. The unknown now is the velocity. Where in a VAV hood, the velocity is known as a constant. A few laboratory pressure control strategies. We involve with room pressurization all the time. Basically moving in a lab environment, we're moving, clean air to less clean air spaces. Normally, lab is negative. It's got fume hoods. We got an offset between supply and exhaust. Tightly sealed rooms will affect pressurization. Room pressure control strategies. Airflow offset control, where you have a fixed difference between supply and exhaust that's maintained through any mode of the lab. You maintain a constant CFM that will deliver you the pressure required for the lab space. You're not controlling off of room pressure, because as we know, open a door, leave the room, your pressure changes, so then you start moving your supply or exhaust to try and catch the pressure change. Where you maintain fixed offsets, you won't be changing the room due to a door opening or someone changing the space pressure. But other forms of pressure control strategies where you would adjust the room pressure, maybe an operating space, BSL, where the pressure, the driving force for that control is the pressure, and you want to adjust it for opening a door, something changing, because you cannot allow any possible neutral situation due to a door opening. So here's a, I guess I'll call it a typical lab space. Fume hoods, temperature control, fume hood controller, room pressure sensor possibly. We're using Venturi valves in this setup. Again, Venturi valves for speed of response and accuracy of airflow and repeatability. And all in this space, there's three components, or there's three control things that are going on simultaneously in a lab environment all the time. Room pressure control, fume hood containment, room pressure control, and temperature control. And that's all simultaneously happening all day, every day. The fume hood is the most important component in the lab space. If the sash is open, the valve will be open, the airflow will increase to make that fume hood safe, and the supply air will increase to maintain pressurization. Temperature control becomes the least priority because I'm not going to change the volume of air coming into that space based on someone being hot or cold. The fume hood needs the air, the fume hood's going to get the air, and then we'll reheat to maintain temperature. So this has 3 fume hoods. Say you had a space with 10 fume hoods, and you walked in, start the day, called a university, and the room was under control, 72 degrees. Everything's wonderful. Hot water coils, 25% open. And they opened every one of those fume hoods at the same time, and they went from, 3,000 CFM to 12,000 CFM. It's going to happen immediately because those fume hoods are going to need the airflow for safety, and the room's going to need the airflow for pressurization control. So the supply will dump that volume of air into the space. So whatever temperature's in the duct is what's coming into that room. So over time, the room will catch up based on the temperature sensor, the sensor variable over there on the wall. But you will get that volume of air and that temperature of air in that duct right now. It's the only way you can do it to maintain pressurization. So temperature is the third priority. Fume hood first, followed by pressurization, which is basically simultaneous. And then we'll make you comfortable after we make sure you're safe. That's the way our VAV labs are controlled. And that's all I had for you guys. Any other questions? All right. No questions. Ask away.